Today I'll be talking about ideal gas laws. I'll provide a link in the description of the video for the material used in this video. We all know matter exists in three physical states: solid, liquid, and gases. Any matter can exist in one of those three forms under different conditions of pressure and temperature. If you looked at this periodic table, you could see the elements that are marked in blue. Those are the elements that are found as gases at room temperature. All gases have the following physical characteristics. Gases assume the volume and shape of their containers. Gases are the most compressible of the states of matter. Gases mix evenly and completely when confined to the same container. This means if we have two different gases, if we put them in the same container, they will mix evenly and completely. Gases have much lower densities than liquids or solids. If you looked at the relation between gas volume and pressure, we name this law as Boyle's law. The Boyle's law states that at constant temperature, the volume is inversely proportional to the pressure of the gas. This means V proportional to 1 over P. If we try to draw the relation between the pressure and the volume, we could see that it represents a curve. If you looked at these two at this figure, you could see that in the first figure I have larger volume, while if I just push the piston down, this means I have a smaller volume. In the larger volume, the particles are spaced out in all direction, and the space between those particles are larger than from the second image, where we could see that the particles are much closer together, because here you could see that the force that of the particles hitting the container is larger in case of the smaller volume than the larger volume. You could see that if I decrease the volume, this means I'm increasing the pressure on the walls of the container. This is why my pressure increases. The second relation is the relation between gas volume and temperature. Charles' law states that at constant pressure, the volume of a gas is proportional to the temperature. This means if I increase the temperature of the gas, my volume will increase. So if if I looked here at this figure, you could see that if I'm increasing the volume, if I'm trying to draw the relation between the volume and temperature, we can represent it as a straight line. Increasing the volume will increase the temperature as well. If I looked here at this figure, I could see that if I have a smaller volume, this means at lower temperature, this means if I heated this those particles or that gas might at this increase by increasing this temperature, the particles will be moving faster and will push the piston upward. This will make my volume increases. So increasing temperature means I'm increasing the volume as well. The relation between temperature and pressure, we name it Gay-lussac law. Gay-lussac law states that at constant volume, my pressure is proportional to the temperature. And the relation also can be represented as a straight line. Now moving to the last relation, the Avogadro's law. Avogadro's law states that at constant pressure and temperature, the volume of the gas is proportional to the number of moles of the gas. This means V is proportional to N. In here, I show you a figure that represents the law of gases that I previously talked about. In the first one, you could see the Boyle's law. In here, I have a certain volume. When I decrease this volume, my pressure will increase because I decreased the distance between those particles. So the impact with the walls of the container will increase. On the other side, if I increase the volume, this means I'm decreasing the pressure. The second figure represents Charles' law. In here, if I lowered the temperature, you could see that my volume is decreasing, and if I increase the temperature, this means the volume will increase, will be increasing as well. Another way of looking at Charles' law, my volume is constant. So if I kept my volume constant, this means lowering temperature will make my pressure decrease, and increasing temperature will make my pressure increase as well. The last figure shows Avogadro's law. In this Avogadro's law, you could see that if I have a cylinder, and if I have this gas cylinder, then I added extra moles of gas. This means I'm increasing the volume as well. And if I removed some of the gas in this cylinder, this means my number of moles inside this cylinder will decrease as well. Moving from that, let's talk about the general gas equation. The general gas equation is actually related to the ideal gas. In ideal gas, we will assume that the volume vary exactly in proportional to the temperature and inversely proportional to the pressure. This means V is actually proportional to T over P. And we also know that the V is proportional to N, so I can remove this proportion symbol by substituting this proportion with a constant. I will name this constant R. R is the gas constant. Now this means V is equal to R Nt over B, and if I move the pressure to the other side, this means that PV is equal to nRT. So we assumed the constant, which is R, the gas constant. But what is the value of this R? For finding the value of R, I have to assume the STP conditions. The STP conditions states that you have 1 mole of gas that will have a volume of 22.4 liter at pressure is equal to 1 atmosphere, and temperature is equal to 0 degrees centigrade, which is equal to 273 Kelvin. So to find the value of R, because I said PV is equal to nRT, this means R is equal to PV over NT. Now if I substitute it with the value at STP, R would be equal to P, which is 1 atmosphere, multiplied by 22.4 liter, divided by N, which is equal to 1 mole, multiplied by T, which is equal to 273 Kelvin. This would be equal to 0.082057. This value have a unit of liter, atmosphere, divided by Kelvin, by multiplied by mole. If I try to round off this value, it would be equal to, the round of this value is equal to 0.082 liter atmosphere over Kelvin per mole. I have to remember one thing: the value of P, when the value of P is equal to atmospheric pressure, my R is equal to 0.0821 liter atmospheric Kelvin per Kelvin per mole. But if I have my pressure in Pascal, this will make my R values equal to 8.31 joule per Kelvin per mole. Now, can I find the change in one of the gas laws parameters? To be able to do that, let's look at R. Like we said before, R is a constant, so R before the change of the volume or the temperature or the pressure of any gas would be equal to P V over NT. So I could say before change it will be equal to P1 V1 N over T1. And if I made a change to the volume or any of those parameters, this means my R would be equal to P2 V2 over NT. T2. You have to remember that the number of moles in both cases would be the same for the same gas. So because R is a constant, I can say that P1 V1 over T1 is equal to P2 V2 over T2. And also correlate BV in RT with another parameters. If I looked at N, I can substitute N with the number, the mass in grams over the molecular mass. And for V, we know that D is equal to mass over volume. The density is equal mass over volume. So I can substitute V with the value M over D. So if I can say B mass over density would be equal to the mass in grams over molecular mass RT. Now I can cancel the mass in grams on both sides. This will make B over D equal to RT over M. And I can say that the density itself is equal to P multiplied by the molecular mass over RT. If we looked at the ideal gas law, it assumes that there is no attraction between any molecules, and the volume of the molecules the volume is ignored during the calculation. But if you looked at the high pressure and the very low temperature, you will find out that the molecules are closer together, and the volume of the molecules is not negligible compared to the smaller container. Also, there will be a considerable attraction forces between the molecules, such as van der Waals or dipole forces, and the attraction forces would pull the molecules together away from the wall of the container. Now, because the molecules are pulled away from the wall of the containers, this will make the pressure lower than in case of ideal gas, and the effective volume is smaller than in case of ideal gas. So what we mean by the term of ideal gas? We mean by ideal gas that my gases have a volume that varies exactly in proportional to temperature and inversely proportional to the pressure. So under condition, real gases differ from ideal gases, because under high pressure and very low temperature, the molecules are brought together, and in that conditions my van der Waals force will have a considerable amount that I cannot neglect during calculation. So my volume is smaller than for real gases is smaller than ideal gas, and my pressure is actually also smaller than of the real gas is smaller than in case of ideal gases. Now let's look at one example. Sulfur hexafluoride is a colorless, odorless, and very unreactive gas. Calculate the pressure in atmosphere exerted by 1.82 moles of a gas in a steel vessel of a volume 5.43 liter at temperature equal to 69.58 degrees centigrade. Because there is no change in the gas properties, we could assume or we can use the ideal gas equation in that case. If I looked at the ideal gas law, it's BV is equal to nRT. And if I rearranged my equation to be able to know the value of the pressure, this means P would be equal to nRT over V. And that would be equal to the number of moles is 1.82 multiplied the value of R in case of atmosphere. I will assume that R is equal 0.0821 multiplied by the temperature. In that case, I have to find out the value of the temperature in Kelvin. This means I will add the value of the Celsius to 273 to be able to get the Kelvin value, and over the volume, my volume in that case is equal to 5.43 liter. That would be equal to 9.42 atmosphere. Let's look at another example. Now let's look at another example. A small bubble rises from the bottom of a lake where the temperature and the pressure are equal to 8 degrees centigrade and 6.4 atmosphere. So this is my T1 is equal to 8 degrees centigrade and my P1 is equal to 6.4 atmosphere to the water's surface where the pressure is equal to 25 degrees centigrade. So this is my T2 and the pressure is equal to 1 atmosphere. So this is my P2. Calculate the final volume of the bubble if the initial volume was 2.1 mil. So if it is 2.1 mil, this means my initial volume V1 is equal to 2.1 multiplied by 10 to the power minus 3 liter. Now I will apply the relation V1 over T1 is equal to P2 V2 equal over T2. So the P1 in that case is equal to 6.4 atmosphere multiplied by the value in that case 2.1 multiplied by 10 to the power minus 3 liter over the T1. I should remember that this is in Celsius, so I have to use the Kelvin, the conversion to Kelvin value. And my P2 in that case would be equal to 1 atmosphere multiplied by V2, which is the value I need to know, divided by the value of the temperature. The second temperature is 25 degrees centigrade. This means if I convert it to Kelvin, it will be equal to, I have to add 273. So by that V2 would be equal to, I can multiply this together and divide them by this value, and the final value of V would be equal to 14 multiplied by 10 to the power minus 3 liter. By that we came to the end of our video. My next video will be about the methods that we can use to measure the atmospheric pressure. Till next time, thank you and goodbye.